Alumni, but for different reasons, because of the demand of good trained statisticians, we have not retained all of them in our country. But during the year end, most of these good statisticians that are somewhere in Europe, in the United States, in Australia, they come back and visit their homes. And we thought that it would be a good opportunity to have these meets at these times when we could utilize the services of these individuals to give lectures to the young statisticians about the things that they're learning when they're out in the world. Now, this has been the model for the last 2 years. This year, of course, because of the pandemic situation, we could not do it in January. But since this is an online event this time, we have been able to get different professors from different ends of the world. And as the meet or the nature of the meet is also evolving, we are also learning how to better place it in front of the participants so that they can get more out of this. And that's why we are hoping that those who will deliver the lectures will talk more about the general background of the topics, general background of the areas that they're learning when they're in United States, in Europe, rather than the most developed research that they're doing on. Because we don't have that technique, and we must learn from the background that they can present in front of us before we get to the level. And the audience is also composed of young statisticians. So we hope that they will give a very broad overview of the topics that they're going to talk about. And I will like to also point out that this year we were not at all sure that whether this event could be held or not, but it has been possible through the support of our director, Professor Sanghamitra Bandyopadhyay, and I thank her heartily for that. And with this, I welcome you all to the third edition of the Young Statisticians Meet. Kiran.
Thank you, Professor Basu. Now I will request our director, Professor Sanghamitra Bandyopadhyay, to address the participants, please.
Welcome to all of you to the Young Statisticians Meet 2021. And again, as I have been told, since the participants are from everywhere, from around the globe, so I don't know how to greet you. Good morning, good evening, good afternoon, whatever it is. It's a good day, I hope, for all of you. And I'm sure the day will become better because we are starting this Young Statistician Meet today, and it will continue till tomorrow. It is actually a very pertinent and very timely thing to happen because our analysis, our studies show that while the world is crying out for trained statisticians, the supply is very low. In particular in India, the quality supply is very low, and therefore the imagination needs to be fired up of the young statisticians, so the young researchers, young practitioners of the statistical methods, because in today's world, I think with this plethora of data in any domain that you can think of, because of huge technological advancements and the large number of sensors which are placed everywhere, huge amounts of data are getting collected. So unless we know properly how to analyze that data with a strong understanding, a strong basis of the subject, we will not be able to do justice. And that is where the Indian Statistical Institute, my colleagues, I'm really thankful to them that they thought that it is extremely important to catch them young, to fire their imaginations so that the youngsters take up the subject, take up the applications, the practices of statistical methods in the real sense, and bring about a change. So, with that in mind, this third edition is being organized now. And of course, the goal is to encourage the young statisticians everywhere, the academia, industry, government, so that they can come together, they can share their thoughts. This gives a platform to collaborate with each other, to network with each other, to know what the problems are and how the best in the field are trying to solve that problem. So YSM 2021 has got together the best of the best from all over the globe, from India and from everywhere else, the teachers who will be discussing, as Professor Basu pointed out, hopefully the basics of what they are doing, so that the youngsters are able to catch and get interested in certain areas. And of course, I'm sure a little bit of introduction to the high level research that our colleagues, or the teachers, the professors are doing in their own domains. A little bit of flavor of that will also be passed on. At the same time, in India, there's a huge amount of requirement in the government also for policy planning, for data-driven policy planning, etc. So I hope this meet and the discussions that happen during this meet will help all of us understand how to solve the problems that face the country and how to solve problems of science in general, because this is the era of data-driven science, where data is driving discoveries in any branch of science that you can think of. And therefore, handling the data, analyzing the data in a proper way is the need of the day, and YSM 2021 hopes to address that issue to some extent possible. I'm thankful to my colleagues, Professor Basu, Professor Kiranmoy Das, Diganto, everyone, that they have put together this meet at a short notice in spite of the pandemic. And there's a huge presence. I mean, I understand about 200 participants are there in this meet. So that is a very big number. And that has been possible also because it is online. People can join from everywhere. That's a good thing about this technology, but I hope we were able to see each other face to face, but I hope next time. So again, with those few words, welcome to the Indian Statistical Institute in the online version. We hope at some point of time we can invite you to the campus and you can be here and look at whatever we have. It's a nice, beautiful campus. I'm really sorry that you cannot be here. But of course, virtually, please do interact with all the colleagues, with our teachers here, with the professors. And I hope you go back, at the conclusion of these 2 days, you are enriched in your knowledge, and your interactions, the interactions that happen during this meet, also leave us enriched. Thank you very much, and have a wonderful 2 days of deliberation, academically fulfilling sessions of a variety of talks. Thank you so much.
Thank you, Professor Bandyopadhyay. And now I will request Professor Diganto Mukherjee, who is also one of the conveners, to please address the participants. Diganto.
Very welcome, very warm welcome to all of you on our virtual YSM 2021. As Professor Basu and Professor Bandyopadhyay has already mentioned, we are really, really happy that we could make this happen. Every crisis creates an opportunity, and this is a nice example of such an opportunity. When the pandemic happened, we were very disheartened that we won't be able to make YSM happen this year. In fact, we couldn't make it happen in January, which is the usual time. But then Professor Bandyopadhyay and Professor Basu enthused us. So Kiranmoy and I took up the challenge, and now here we are. In fact, we have managed to get a good participation in the conference, a very good panel of speakers. So apart from the fact that we are not able to welcome you physically on campus and treat you to some sweets in Kolkata, I think this conference is going to be a great success. I don't think I have much to add apart from the common instructions that when the talks are going on, please keep yourself on mute. You can use the chat box during the talk and ask questions at the end. But of course, Kiranmay will be there, who will be anchoring and helping you all through this process. The speakers are, some of the speakers from the morning session are already here. A very good day to you, because I know that it's late in the evening or even night, but you have been kind enough to come and deliver your talk in a short while. So without any further ado, I will hand it back to Kiranmay, only saying that enjoy yourselves over the next 2 days. Thank you.
Thank you, Professor Mukherjee. So with this, I again thank the chairperson, Professor Ayanendranath Basu, our director, Professor Sanghamitra Bandyopadhyay, and of course, our convener, Professor Diganto Mukherjee, for addressing the participants. So with this, we basically end the inaugural session, and our first technical session, which is Monte Carlo methods on data science, will just start in 5 minutes. So please give us 5 minutes and we will start this session at 9:20. Thank you all. Please be here.
Can you see my screens?
Yes.
Okay, good. Thank you. Okay. Here's a brief outline of my talk. I will first begin with describing the Monte Carlo integration problem. And in particular, I'll be talking about what is known as Markov chain Monte Carlo methods. And one such algorithm, or rather, it's an idea, Metropolis Hastings algorithm, and it has many variants. I hope to talk about some of these variants today. And although throughout my talk at the beginning, I'll be looking at mostly toy problems, I hope to talk about concrete problems involving what is known as spatial generalized linear mixed models. And I'll be applying these algorithms that we'll be talking about to study these models. Okay, so let's look at this Monte Carlo integration problem. So we have a probability distribution pi. So pi is a probability distribution on some space S. We have a function h that's of interest, and we know that h is integrable with respect to pi. So that is, we know that this integral exists and it is finite. But what we don't know is its value. So we know it is integrable, it's a finite number, but we do not know its value, and we cannot, it is analytically intractable in the sense that, you know, we just can't take a piece of paper and a pen and and integrate this. So that means we have to be thinking about some approximations, some methods to approximate this integral. Now there are different approaches. There is numerical integration methods, there is analytical approximation methods. But today I'm going to talk about what is known as Monte Carlo methods. So Monte Carlo methods for approximating this integral, getting an approximate value of lambda. The classical Monte Carlo method, or the ordinary Monte Carlo method, is this. Suppose we can simulate from pi, that is, we can get IID observations from pi, then we can calculate what is known as the sample average or the sample mean. So we basically sum the values and divide by the number of observations. Let me denote that by HN bar. Now see, this lambda can be thought of, I mean, it's exactly what in statistics we call population mean. So lambda is the population mean, HN bar is the sample mean. So the Monte Carlo method, the ordinary Monte Carlo method is you estimate the population mean by the sample mean. Now, the justification of this method is due to the law of large number, which says that if we have large enough sample, then the sample mean is close to the population mean. Okay? So if we have collected large enough sample, the sample mean will be close to the population mean. Okay, let me give a toy example. Suppose pi is this function. Now, you know, we in statistics we can immediately see that oh, that's the standard normal density, the bell-shaped curve with mean 0, variance 1. Now, suppose the two functions, I consider two functions h with either x or this indicator function x bigger than 1. So that means if h is the identity function x, that's the mean of pi, or it is the tail probability, that probability, the shaded region. Obviously, you know, we know these values. I mean, we know the mean. We don't need to need to think about any Monte Carlo method to get this value. We know analytically the mean, but let's see. Suppose I get 50 observations, 50 normal standard normal draws, and calculate the mean. So this is, I mean, I calculated that, and those are minus 0.06, 0.16. So those are estimates of the true values of lambda. Now, naturally, when we give an estimate, so this is just an approximation, so we want to have an idea about how much error we are making, you know, how much error is there. Well, we can answer that question, you know. To answer that question, we can use what is known as the central limit theorem. So central limit theorem says that if h has finite second moment, then if you multiply the error by square root n, it goes converges in distribution to a normal distribution with variance sigma square h, and we have a consistent estimator of that variance. So in the sense that you know, this sh square, which is the sample variance, indeed actually converges to sigma square h, that asymptotic variance in the central limit theorem. So just using this idea, we can actually construct a 95% confidence interval for the mean. See, I'm writing e pi h here. That is basically lambda, because you know the lambda, remember from my previous slide, is indeed the mean of the function h with respect to pi. So I'm here writing here e pi h. So a 95% confidence interval is, you know, I can calculate this by, you know, adding and subtracting 2 times the standard error. Now, the width of this confidence interval, or the half width of this confidence interval, gives us an idea about how much error we are making, how much error, you know, we can basically attach an error to this estimate, HN bar. Not only that, we can also use this confidence interval to determine whether the sample size that we have the samples that we have collected, whether that is large enough or not. If the, you know, so for example, we have an idea about, well, you know, we want this much precision, that is the width of the confidence interval should be lower than that. So we can use that and do a simple sample size calculation using our pilot estimate of the sample variance. We can do a simple sample size calculation to determine what is an appropriate value of n to achieve the desired level of accuracy. Indeed, I calculated the confidence intervals based on those 50 samples, and those are this for the 2 functions h. And you may think, someone may think that, well, this confidence interval is too wide. Well, the nice thing about Monte Carlo method is that we can increase the sample size and reduce the error. So I increase the sample size 10 times 500, and as you can see, the error is smaller. The width of the confidence interval is less if the confidence interval is narrower. Okay. Now, so this is my discussion on classical Monte Carlo method. Now, the thing is, so as we saw that the classical Monte Carlo method hinges on the fact that we can efficiently sample from the distribution pi. It turns out in the modern days, in the complex pies, the complex models that we are handling, there is, most of the time, there is no efficient method to make draws, to make exact draws from pi, to make IID draws from pi. So then, in that situation, we may be able to use what is known as Markov chain Monte Carlo method. So I'm writing down my problem. Remember, I have a probability distribution pi, I have a function h, which I want to integrate, or I want to get an approximate value for this integral. The ordinary Monte Carlo method is calculate the sample mean, but we cannot get IID draws from pi efficiently. What Markov chain Monte Carlo method does, it replaces this IID draws by what is known realizations of what is known as a Markov chain, which satisfies some properties. Well, what are the properties I need? I need the pi, that my target distribution pi, to be the stationary distribution for this Markov chain. See, Markov chain is basically a sequence of dependent random variables, but the dependence is a simple type of dependence is in like one-step dependence. That is in the sense that, given the present and the past, future only depends on present, just one step. And pi is a stationary distribution for this Markov chain. It means that, if you can start the Markov chain at pi, then marginally every draw, that is, if x1 is a draw from pi, then x2 will be drawn from pi. Marginally, all of the random variables will be drawn from pi. They will be correlated. They will be dependent sample, but marginally all of the same distribution pi. But you might say that, if you can start from pi, then why do you need Markov chain Monte Carlo? Yes, we will never be able to start from pi, and we don't need to start from pi. The idea is that if you ever reaches pi, then you will always be at pi. So that's the idea. And we also need that this Markov chain is appropriately irreducible, in a sense that, starting somewhere, it can go anywhere in the space. So remember, this Markov chain is traversing on this space S. So starting somewhere, it can go anywhere with positive probability in some iteration. May not be in the next iteration, but in some iterations it will reach there. So that's what irreducible means. And it is very easy to construct such Markov chains, and I'm going to show you a bunch of them today. Now, for such Markov chains, there is a law of large number for Markov chain, which says that if you replace this IID draws in my HN bar, if you replace these xi's by the realizations of the Markov chain, that is indeed consistent. So that HN bar is also HN bar also converges to lambda as n tends to infinity. So we can use it. So let me show you some a class of algorithms which you can easily construct, which has pi as a stationary distribution, and you can use this. So indeed, that is why MCMC is so popular. So because it is very easy to construct. So here is a construction. Let pi be my target distribution, as I said. And remember, a Markov chain is just one step dependence. So if I tell you how to make one step, you can just repeat this step. Like you can go back to your office and just repeat this step again and again, and you have the Markov chain. So I just have to tell you how to make one step, how to make one transition of the Markov chain. So let xn be the current value of the Markov chain. So the Metropolis-Hastings algorithm goes like this. So I draw y from some density q, okay, some density q, some densities. You can think of this as the conditional density of y given xn, right? The regular conditional density we have studied. So I draw from some q, okay. Now this pi doesn't have to be any stationary. It doesn't have to have anything to do with q, in the sense that it doesn't have to be stationary for q. So what I do is I do a correction, this accept correction. So I propose a y using q, and then I accept it with certain probability, and that probability is given right here. Okay, and if I if I don't accept it, I stay where it is, I don't move. And if I accept it, then I move to that point. So this is how one step of this Markov chain takes place, and then obviously you repeat it again and again, and you run the Markov chain. Okay. Now, so this is as I said, it's a class of, it's one idea, but it's class of algorithm, because I didn't tell you anything about Q, right? And all these chains will have stationary distribution pi, and under very weak condition, this is also irreducible. Okay, so so basically any Q you can use. Okay, but obviously some Q will be better than others, right? But in what sense better? Hopefully I'll be able to talk about that a little bit today. So there are two special Qs we can use. One is when Qy given x is Fy minus x. So that is known as the random walk metropolis chain. So basically, so x is my current state. My next step y is simply x plus I. I is the increment, okay, where I is drawn from some distribution f. And if that f is symmetric, that acceptance probability alpha doesn't depend on Q. Remember, so my general acceptance probability depends on Q, but when f is symmetric, that acceptance probability is not going to depend on Q. Okay, so that's called random walk chain. And independence chain is where this candidate density doesn't depend on my current value. Okay? So f doesn't depend on my current value. Qy given x is Fy. Now, let me run this random walk chains in a simple toy example. Again, my target distribution pi is the standard normal density we looked at in the first slide. And I consider my proposal distribution. Remember, I add a noise to my current value, right? And that noise is drawn from a normal density with mean 0, obviously, and variance sigma square. And I can easily calculate the acceptance probability, so I can run this chain. So I ran this random walk chain for 3 different values of sigma. And I am showing some plots here. The plots in the first row are what is known as the trace plot. So that is basically, it's a time series plot. I am plotting the Markov chain realizations against the iterations. And the bottom plots, the second rows, what is known as the autocorrelations. See, Markov chains are like correlated. What I am plotting here is the lag k correlations versus k, versus the lag. Now, let's look at when sigma, as I said, I consider 3 values of sigma. The first one is sigma 0.1. That is my leftmost plots. You can see the chain is kind of sticky. It doesn't move much. And why? Because sigma is small, so you are making only small jumps. So the chain doesn't move. So most of the proposals, most of the candidates are going to be accepted because you are making only small move, but you don't move much. So that's why the autocorrelation will be high. When on the other hand, when sigma is 20, that is the variance, the proposal variance is large, you are going to make large proposal, but most likely those will be rejected because those are kind of in the tails of the target distribution. So that's why you see a lot of flat lines in the trace plot, because a lot of proposals are rejected. And if they are rejected, the chain doesn't move. So that's why autocorrelation will also be higher. Whereas when sigma is like in the middle, 2.4, you can see the chain is moving, the autocorrelation is also dying down pretty fast. So that is kind of in the, on the right side. Okay. So the sigma, too small, bad, too large, bad, middle, okay. And what I wrote at the caption is that acceptance rate of the 3 chains. So you see the first acceptance for the first chain, acceptance is too high because you are going to get accepted a lot. The middle portion acceptance is too small because you are going to be rejected a lot. And the last one is around 40%. Okay, now for the random walk proposals, the proposal density is a normal density which is centered at x, the current value, and with some variance. And in higher dimension, it will be some variance covariance matrix. So you see, the proposal density does not involve the target density that we are trying to explore. So the naturally people thought of, well, can I think of other algorithms where the proposal density depends on the target? So one such algorithm is known as the metropolis adjusted Langevin algorithm, where you can see the proposal density has the mean, it depends on the gradient information of the log density, log target density. Okay. Now, why it is called mala? Well, in the continuous time, there is a continuous stochastic process known as the Langevin diffusion, which is this. Well, so xt is the stochastic process and wt is the Brownian motion, the d-dimensional Brownian motion. So that is why it is called the metropolis adjusted Langevin algorithm. Now there is an unadjusted version, and this is the adjusted version where you use the acceptance probability. Now, as I said, the Mala, for the Mala algorithm, the justification or the intuition comes from the Langevin diffusion. Now, we don't have to use the identity matrix for the variance covariance matrix. In fact, for a general stochastic differential equation with a general drift vector B and general volatility matrix sigma, there is the Fokker-Planck equation, which gives you the evolution of the probability of the probability density of xt, and in particular, if the probability density doesn't change, then you have a stationary chain in the continuous time. So using that idea, there are other versions of Mala algorithm has been proposed in the literature, where you use, say, for example, instead of using a identity variance covariance matrix, you can use some matrix G. Now, obviously, so basically, you can think of when the coordinates of x are correlated or they have different variances, then I want to, instead of using the identity matrix, I want to use some G. Obviously, you can use any G, but some G will be better than other. Now, in the preconditioned Mala algorithm, the G matrix doesn't change or doesn't depend on x, the current value. So there are other versions of Mala algorithms. So for example, something called manifold Mala, where G depends on the current value. Again, the name manifold comes from because there are some, so there are some choices of G which has, which can be thought of they have some connection with some, diffusion on some manifold. Okay, let me stop there. Okay, now I want to use these models. So far I have used only, so I have, okay, so I have only so far used on toy examples. So let me give you a more concrete, practical example. So this is known as what is known as spatial generalized linear mixed models. So suppose D is a spatial domain of interest, and let XS be a Gaussian random field with some with some mean function and some covariance function. Now this covariance function is going to depend on the distance between S and S prime. So S is the the location. So covariance function is going to depend on that S and S prime. So in practice, these mean functions and the covariance function will not be known. So for example, the mean functions of will most likely be depending on some covariate informations, and the covariance function, you will be using some parameterized family, and then that parameterized family will have some unknown parameters to estimate and stuff like that. But for the talk today, for the purpose of the talk today, I'm going to assume that the mean and the covariance of this Gaussian random field are unknown. Okay, but we do not get to observe this Gaussian random field. What we observe is a measurement process Y, which we are going to assume that this Y given X, this latent process X, are conditionally independent. And in particular, for today, I'm going to assume that y given x has binomial distribution with where the mean of the binomial distribution is related to the underlying Gaussian random variable, the latent field, the latent process, which you don't get to observe through the logit link. Okay. Now, for this, suppose you want to calculate the likelihood function. So the likelihood function, well, you know, the likelihood function is this, that, you know, the binomial PMF, the product of them, and phi m is that Gaussian density, right? Suppose H1, H2, Sm is my observed locations, and we have a Gaussian density and integral of that. So you see the likelihood function is not available in closed form. So, you know, even when we assumed that the means are known, the coeficients are known, the special GLMM, the likelihood function is not available in closed form. So what I'm going to do today, so I am going to consider the posterior density of x given y. You know, I have, you know, so I can consider the posterior density of x given y, and suppose I want to sample from this posterior density. Okay. Now, I am going to consider a simulation example. Now, you know, since the only thing is that since I'm assuming this mean and covariance functions are known, so that's why I cannot do a practical example. But this special general dynamics model is, you know, very popular. For example, say, you know, if you're interested in agriculture or precision farming, so you want to say, suppose you want to get a map of the some kind of disease severity, right? And so in one location, your y may be the number of plants infected by that disease. Okay, so you have that binomial distribution given an underlying spatial random field, and you want to make a prediction map. You want to make a disease severity prediction map. So this is, you know, this is a spatial GLMM is a practical model. It's used a lot, but for this talk today, I'm going to assume a simulation example, just because, you know, I'm simplifying things here. So what I am considering here, I am considering a 0, 1 by 0, 1 grid, and, you know, oh, what happened? And I don't know. So, and then, I'm considering a 21 by 21 square grid. So out of that, I have 300, I'm choosing 350 randomly chosen points. And I ran different algorithms that we have talked about today. And here is the performance comparison of these algorithms. So for example, I talked about these Mala algorithms with, with different, with G. So I use different choices of G. So one is the identity choice, or I can use the prior covariance matrix, or I can use I hat. So I hat is some kind of a Fisher information matrix. So I can use some I hat inverse. And you can see here, so what I'm doing here is for the first 175th and 350th location, I calculate what is known as the effective sample size, which basically tells me, you know, how many IID samples, because, you know, NCNT samples are dependent, right? How many approximately independent samples you are getting from it. So the larger the number ESS, the better it is. And so that's my, you know, third column. And then the fourth column is giving you, so different algorithms takes different times. Like, see, for example, for random walk, you don't need any gradient calculation. So that will be run faster. Whereas for Mala, you need the gradient calculation. For M Mala, it is even more complicated. So the time it takes is longer. So I'm calculating per unit how many effect samples you are getting. And then the last column is what is known as the multivariate ESS, multivariate effective sample size, including for all of them. So you can see when I choose from this, you can see that when I'm choosing G to be I hat inverse, then I get the best performance out of all these algorithms. Okay. So again, so if I just consider the diagonal elements, that's not good enough. I have to consider the, you know, whole that again I had is some kind of Fisher information matrix. So I must admit that, you know, this is from a PhD thesis from one of my students who is working here right now. Okay, so and again, so this is the autocorrelation plot for these algorithms, and you can see that that particular G, you know, I had inverse for which the autocorrelation plot, you can see that it decays very fast compared to other algorithms. Okay, so this is my last slide. So I have talked about that, so Markov chain Monte Carlo is easy to implement because, all this there are lots of queues, lots of choices you can implement, and there are a lot of software packages which are out there. You can use it to run the Markov chain to get the estimates, to approximate your mean. So that is why it is so popular. But how do we become responsible for our estimate? As I said, in the context of ordinary Monte Carlo method, I want to have some kind of idea about how much error I am making, right? So in this case also, if I have a central limit theorem, I can do that. If I have a central limit theorem and a consistent estimator of the asymptotic variance, I can do that. So note that the asymptotic variance here, I'm including P, because so P is the Markov chain. It stands for which Markov chain? Remember, all these different Markov chains, they all have the same stationary density. So I can use any of them to estimate the mean. So, but the asymptotic variance will differ from one choice to other. And obviously, I want to choose that Markov chain which leads to smallest error, that is smallest asymptotic variance. Now, how do I, and then obviously, if I have that, then I can calculate the confidence interval and so on and so forth. The bad news is that unlike classical Monte Carlo method, just mere existence of second moment doesn't guarantee central limit theorem. So being responsible is not that easy, in MCMC. So what we have to do, we have to make sure, this is a sufficient condition, that if you can make sure that your chain converges fast enough to the stationary distribution, then there is a central limit theorem. In particular, if the chain is geometrically ergodic, which means that the chain converges at exponential rate, then there is a central limit theorem for all square integrable functions. Again, for the chains we have discussed today, for all square integrable functions, you have a central limit theorem. Okay, and now the other thing is that once I establish the central limit theorem, I also have to find out a consistent estimator of the asymptotic variance. You see, the asymptotic variance is a little complicated here because it involves, it's an infinite series, it involves all the lag covariances. So I have to be able to estimate these covariances. Now, this is where I want to kind of relay this to my second speaker. In fact, the second speaker is going to talk about geometric ergodicity for certain algorithms for Gibbs sampler, which is another very popular MCMC algorithm, although it can be thought of as special cases of metabolic resistance algorithm. Now, so so we need geometric ergodicity to establish central limit theorem. So that is the importance of this kind of study. And there are a lot of works going on studying this. In fact, Lizin, whose work I presented, so she has established general results for establishing sufficient conditions for establishing geometric ergodicity for these multi-type algorithms. And not only that, then she verified that for this binomial SGLMM model, those conditions are actually hold. Okay, and then for consistently estimating these asymptotic variances, we need to estimate these lag covariances. And the third speaker is going to talk about how to estimate these lag covariances efficiently. Okay, so this is where I end. Any question or?
Yeah, so thank you, Dr. Rai, for a very nice illustrations and very nice talk. I just see a couple of questions in the chat box, and I'm just reading these questions and I'm requesting you to answer. The first question, I think it came when you are discussing the metropolis systems algorithm. The person is asking whether the Markov chain should be aperiodic as well.
Oh, that's a good question. So yeah, for consistency of the estimator, you don't need aperiodicity. Okay, but obviously for the convergence of the distribution, you need aperiodicity. But for this strong law of large number, you don't need aperiodicity. No.
Okay. And another question is when you are discussing Mala, the question is there an intuitive reason why a common scaling factor H appears in both the mean and variance expression in Mala?
Yeah, that's a very good question. So in fact, see, so yeah, you can take age to be 1, but the thing is that you need to take the age to be the same. That basically comes from this Fokker-Planck equation. You need to have this equation has to hold. So that's why you have to put the same age. Okay, so you can take age equal to 1. You can, but you have to put the same age there. You cannot put age there and age by 2 there. Well, that is okay. That's for the Fokker-Planck equation to hold. Okay. Now, for the invariance of the MCMC algorithm, you don't need it because you are using a metabolic Hastings algorithm. For the Fokker-Planck equation, you need the same age. Now, the reason for practical purpose why we use this age, because that age we can use to get like that is the one we can change to get certain acceptance rate. So that's the idea.
And the last
I'm hoping that I'm answering the questions, because I can't see the question. So yeah. If there is
otherwise the person who asked the question should interrupt you. So since there is no interruption, so I'm just guessing it's fine. The last question I see here.
Can I ask it's actually like a follow-up? Yeah. So Dr. Roy, so H is like a tuning parameter, right? You vary it and you check how your acceptance rates and how your trace looks, right?
Mm-hmm.
So is it easy to tune, and do you have to spend a lot of time tuning it, or or there are some rules of thumb?
No, rules of thumb mean you want to basically get a nice looking test plot, nice looking nice acceptance rate and stuff like that. So but that depends on what G you are using, So and obviously the data set, I mean, there is no there is not one age going to hold for all choices of G or all choices of model or all choices of data. It is specific to the example that you are working on. Does that answer your question?
Yes, it does. And just what if say your parameter space is somewhat high dimensional, having a variance covariance matrix probably might have a huge computational cost.
Yes,
wouldn't it? So how do you choose when to go for identity and when to go for the inverse of your the Fisher information, that kind of thing? Is there some guidelines for that?
Well, yeah, no, unfortunately, I won't be able to give you a guidance for this. So as in this example, we showed that, well, in this case, we could get some kind of a Fisher information matrix. You won't be able to get it. For example, if I consider the general model that I talked about here, where you have the covariance functions unknown, in those cases, you don't have the Fisher information matrix, okay? So, yes. So there has been some intuition, some justifications of using some kind of Fisher information matrix, and that's why I said the name M comes from M mala, manifold mala, but you may not be able to get that. Okay, so yeah, I mean, so if you can get that, you use it. If you don't get it, you use the something else. So for example, we also tried sigma, but that doesn't work that well, because that is not, the prior variance is not including the information from the likelihood. And this is the spatial model, the likelihood is informative, and so that's the problem. So yeah.
Thank you. That answers all my questions.
So there is one more question in the chat. You don't mind?
Yeah, no, I'm just wondering, like, should we just take these questions and stop and then keep all other questions for the last time?
Yeah, I think it's better, because we are like getting close to 10:30, 10:28 now. I mean, their time is 10, right? So
yes.
So it's better to, I think, move on.
Just one last question we just take, and then we just I just hand it over to you, and you can continue. Okay. So I think the last question, as it said, in Metropolis Hastings algorithm, we have dependent observations, but when we want independent observations, how can we modify Metropolis Hastings?
No, so when you run a Markov chain, you are not going to get independent observations. You are going to get dependent observations. When you are running any Markov chains, you are going to get dependent observations. So otherwise, you go for rejection sampler. Like to try to get independent draws, like a rejection sampler or something. But image algorithm is not going to give you independent draws.
Okay, so I guess we should stop here. And now I request Vivekananda to chair the other two talks. And I'm there anyway, but so.
Oh, that would be great, because I don't know how to read this. Maybe I'll be able to read later on.
No, I'll be there. So you will just introduce the speakers and just, take care of all other formalities.
Thank you, Kiran. Okay. Okay, our next speaker is Kshitij Khare, who is an associate professor in the Department of Statistics at University of Florida, my alma mater. And it is nice seeing you, Kshitij. And so for the sake of time management, I hand it over to you now, so you can start your presentation.
All right, thanks, Vivek. Let me share my screen. All right, so I want to thank Vivek for nicely setting up my talk with this introductory material on MCMC and geometric ergodicity. So what I want to talk about today is a result for geometric ergodicity of a Gibbs sampling algorithm, which is an MCMC, a Markov chain Monte Carlo algorithm for something called the horseshoe. Okay, so here is, wait, I'm having some trouble going up and down. Oh, there we go. All right, so here is the plan for the talk. So what I'll, as Professor Basu said, I'm going to try and spend a lot of time on the background material here, and then just give you a little bit of flavor of the new research at the end. So I'm going to start by reviewing what this horseshoe is. So it's basically a prior distribution that has been developed for high dimensional linear regression. So after reviewing that, then we will talk about how to do posterior computation for this prior. And Vivek already talked a little bit about this. We'll also talk about what's the importance of establishing geometric ergodicity for any MCMC algorithm, what it gives you, why it's important. And then I'm going to talk about this new result that we have for a Gibbs sampler for the corresponding to the horseshoe prior. And then I will end with a little bit of a simulation experiment. All right. So just to mention this, the result that I'm going to present is joint work with my current and former student, Shumon and Shubhodeep Pal. All right, so let's get started. So let's think of our basic simple linear regression model. So we have y is x beta plus sigma times epsilon. So y here is your n-dimensional response. That's why I say it's in r to the power n. X is the design matrix, n by p. Beta is your p-dimensional regression coefficient vector. Sigma is the error variance, and epsilon is the vector of errors, let's say normal 0, 1, all right? And what we want to do here is we want to estimate beta and sigma squared. And remember, so beta is this p-dimensional vector of regression coefficients, right? So over the last couple of decades, interest has shifted because of the kind of data sets that we were getting, starting from genetics and then in many other areas, where the sample size n, so n is a number of responses, was either of the same size or much smaller than the number of predictors p in the problem, okay? So number of regressors. So this is called the high dimensional setting, where your number of predictors is much more than the sample size. So you have too many parameters to estimate and too few samples, right? And if you want to do meaningful statistical estimation or inference in this kind of a setting, you need some kind of regularization or shrinkage or parameter reduction, right? You just cannot estimate 10,000 parameters with 100 samples, right? It's just not realistic. You have to reduce the effective number of parameters in some way, okay? And so in the frequentist domain, the approach that people came up with was, well, what do you generally do in statistics? The most standard method of doing estimation is maximum likelihood estimation, right? You take the likelihood and you maximize it, or you take the negative log likelihood and minimize it, the same thing, right? So what they said is that because you are in this extraordinary situation where you have too many parameters, instead of minimizing, so small l here that you see is the negative log likelihood, right? So if I was in the standard classical setting, I would just minimize this negative log likelihood small l, right? But now, because to adjust for having too many parameters, instead of minimizing the negative log likelihood, I will minimize the negative log likelihood plus a penalty function in the parameters beta, right? And so what kind of penalty functions were typically chosen? Well, here is the more older one, which is the ridge regression. Many of you must be familiar with this. Essentially, you just, this penalty function is just the sum of squares of the entries of beta, or summation beta j squared, multiplied by what we call as the penalty parameter, which determines how much weight you are giving to the penalty, right? And so this it introduces regularization because it shrinks the value of these beta j's, but it does not set these parameters exactly equal to 0, right? And that might be desirable in some applications. And so in 1995-96, Rob Tibshirani introduced the lasso, where instead of having the sum of squares of the betas as a penalty, you have the sum of absolute values of beta as the penalty here. And what this does for you is, in addition to, of course, introducing some sort of shrinkage, the minimizer of this function, you minimize this function with respect to beta, the minimizer has many, many zeros, typically, okay? The number of zeros depends on how large lambda is. And so you get exact sparsity or exact zeros in your estimate, the minimizer of this problem. And that can help you select the variables which are important, or the predictors which are important, and it can help you throw out the predictors which are not important, right? So that's the approach that was taken in the frequentist domain, and there is a lot of extensions to it, but these are the most basic and standard ones. So let's move on, and there is a duality between this regularization and Bayesian modeling. So what is this regularization doing? It's saying, well, you minimize with respect to beta the negative log likelihood plus this penalty function that you add, right? So it's an optimization problem that we are solving. Well, it can also be, so this minimizer of this optimization problem can also be interpreted as the posterior mode in a Bayesian model, where my prior is chosen as the exponential of the negative of the penalty function. So it's not hard to see that if I have a Bayesian model where the prior is chosen as the exponential of the negative of this penalty function, whether it's the lasso penalty or the ridge penalty, the corresponding minimizer corresponds to the posterior mode for that Bayesian model. So there is that little bit of a Bayesian connection to this regularization. But so as I said, if you want to do the ridge penalty, that corresponds to putting a Gaussian prior on each beta j. Beta j is the jth entry of beta. And if you want to put the lasso penalty, also the L1 penalty, that corresponds to putting an independent Laplace prior on each entry of beta or beta j, right? But in the Bayesian world, the approach that was taken for this high dimensional regression, the standard approach, was the so-called spike and slab prior. Okay, so what you do is, so you want to fit a Bayesian model, right? So when you want to fit a Bayesian model, you have to come up with a prior distribution. Now here we want priors which will introduce sparsity in the coefficients or the entries of beta, right? So what you do is, for each entry of beta, you put a mixture prior, a mixture distribution as a prior. So one component of this mixture is a discrete mass at point mass at 0, and this will introduce exact sparsity or zeros in the coefficient vector. And then the other, so this discrete mass at 0 is known as the spike, right? And then the other component in the mixture is a kind of a diffuse or a heavy tail density, absolutely continuous density, which is known as the slab. And this is to model the significant or the non-negligible entries in the coefficient vector beta. So this is a good approach in the sense that it induces exact sparsity and therefore useful for variable selection. Variable selections means which of these coefficients is significant for predicting the response, right? So that's so this kind of a prior is useful for that. But the flip side is that because of this kind of discrete mixture that you use, it faces many computational challenges. So computationally, it is it's very challenging, and especially in the context of high dimensional problems where you have 1,000 or 10,000 or maybe even 1,000,000 predictors, it's just not feasible to sometimes to run this approach. So what was an alternative that was proposed, and it has become really popular in the last decade or so, is the so-called global local shrinkage prior. Okay, so instead of putting this discrete spike and slab prior, we are going to put a continuous prior on each beta j, right? And so here is how this prior looks. Okay, so it's a hierarchical prior, right? So what we do is we introduce these additional parameters lambda. Lambda is a vector of parameters, lambda 1 to lambda p, right? And tau squared. And here is what we do. So given lambda at tau squared and sigma squared, remember sigma squared is the error variance. The distribution of each beta j independently is a normal distribution, right? The mean is 0. And the variance is sigma squared, the error variance. That's fine. And then we have tau squared times lambda j squared. So the conditional variance of, this is the prior, right? So the conditional prior variance of beta j is sigma squared times tau squared times lambda j squared, right? So the idea here is that this tau squared is thought of as a global shrinkage parameter, right? Which means it controls, it shrinks the coefficients towards 0, okay? Because what we want to do ideally is coefficients which are negligible, we want to shrink them towards 0, and coefficients which are significant, we do not want to shrink them so much. That's the goal here, right? In order to select which ones are important, which variables are important, and which variables are not important, right? And so lambda j does this role. So lambda j is called the local shrinkage. So lambda j depends on j, obviously, and so basically lambda j helps in identifying the signals and making sure that they are not shrunk too much, right? So if, for example, if the jth predictor is significant, then perhaps lambda j will help not shrink the beta j too much. That's the hope here. All right. And then, of course, you put a prior f on each lambda j independently, and you put a prior g on the global shrinkage parameter tau squared, and then you put some prior h on the error variance sigma squared, right? So this is basically the kernel for the global local shrinkage prior, right? And the choice of f and g, of course, is extremely crucial. It will determine how good or bad your prior is in attaining your goals, right? So, but you have to note here that this is a continuous, if you look at the marginal prior of beta j, if you marginalize out lambda and tau squared, it's going to be an absolutely continuous prior. There is no discreteness here. There's no discrete mixture, nothing like that, okay? And so the great advantage that we get with these global local shrinkage priors is that they are, you can do much more efficient computation in high dimensional settings vis-a-vis the spike and slab prior that we talk about with the discrete mixture, right? Of course, the flip side, there is no free lunch, right? So the flip side is that you do not get exact sparsity in the betas, right? So you don't get exact zeros and non-zeros, which help you immediately choose which betas are significant and which betas are not significant, right? But if desired, variable selection can still be performed by thresholding you compute the posterior means and medians for each of these beta j's, and you can threshold them, or you can examine the corresponding posterior credible intervals and then do variable selection that way if you want to, right? So, in the last maybe 10 or 15 years, a variety of global local shrinkage priors have come up in the literature, okay? All of them have this form. They only differ in what f is and what g is, okay? So for different choices of f and g, people have proposed various, and there is more, but these are kind of the more standard ones. So this is kind of a reduced list that I'm providing to you. But today I want to focus on perhaps the most widely used and popular of these global local shrinkage priors, and that is the horseshoe prior, which is number 2 in this list. All right. So what does the horseshoe prior do? Well, as I said, all the global local shrinkage priors have this common structure, that beta j, each beta j given this lambda and tau squared has this kind of a normal distribution, and then you put priors on lambda j and tau squared. Lambda j's are the components of this vector lambda again. So what the horseshoe prior does is it chooses for each lambda j are your local shrinkage coefficients. It chooses, or local shrinkage parameters, it chooses a half Cauchy prior. So C plus 0, 1 is the notation for the half Cauchy prior. So it's the Cauchy prior restricted to the positive real line. Okay, and it's a so Cauchy 0, 1, right? And for tau squared, again, we are going to leave it as a general G, but many people like to also choose the half Cauchy prior for tau squared as well, and they refer to that as the horseshoe. But for this talk, the horseshoe prior is any global local shrinkage prior which chooses these lambda j's, the local shrinkage parameters, to be half Cauchy. All right. So why is this good? See what you can easily check. So if you find out the marginal distribution of beta j, if you integrate out the lambdas, right, and if you find the marginal distribution of beta j, then what you will see is that this distribution has an infinite spike near 0. And this spike is basically like minus log of absolute beta j. Okay, so you can see that it jumps to infinity as beta j approaches 0, right? And this marginal of beta j near infinity has a fat tail, has a polynomial tail. It behaves like 1 over beta j squared, right? And these two are very desirable properties, because see what a big spike at 0 and a fat tail near infinity helps us do is it helps us aggressively shrink the insignificant coefficients to 0, and it helps aggressively not shrink or not touch the really significant coefficients. So so having these two properties introduces the much desired for dichotomy that we want, where that in the end the coefficients which were kind of negligible, they will be shrunk towards 0 aggressively, which will help us identify and then remove them from the model. And the regression coefficients, which are indeed significant, they will not be touched much at all. And so they will remain strongly in the model, and it will help us identify them and keep them. Okay. So this is a very much desired property that this prior is able to satisfy. And the other priors that were up there in the list, for some reason or the other, they are not as good. So that's one of the reasons of the popularity of the horseshoe prior. Okay, so this is exactly what I said in the previous slide, that this heavy-tailed half Cauchy priors make sure that the significant coefficients are not regularized or shrunk at all. Okay, so that's all this slide is saying. That's the key strength of the horseshoe prior. That's a key reason for its popularity, right? So when I heard this name, this was maybe a decade ago, the horseshoe prior, I wondered, why are they calling it the horseshoe prior, right? So let me tell you why they call it the horseshoe prior. So let us consider a situation where where P is equal to N. So the number of predictors is exactly same as the sample size, and my design matrix X is just the identity matrix. Okay, so that's called the normal means problem. So essentially, this is my model. Y equals beta, because X is identity, plus my sigma times the error vector epsilon, right? So if this is the case, then what one can easily show is that the expected value of beta j, the jth entry of beta given y, or in this case, it just depends on yj, is equal to, it's basically yj itself times this coefficient, right? And what is this coefficient? It's 1 minus expected value of kappa j given yj. Now, what is kappa j? Kappa j is nothing but this function of the local shrinkage parameter lambda j. So kappa j is 1 over 1 plus lambda j squared. Okay. So in this particular situation, the posterior mean of beta j is just yj, the jth response value, times this coefficient in terms of kappa j, where kappa j is 1 over 1 plus lambda j squared, right? And so if kappa j is 0, that means that you have no shrinkage at all, because it will just be yj. And if kappa j is 1, then you have total shrinkage to 0. Okay. And what happens is that, on lambda j, we have this half Cauchy prior, right? So if I look at the induced prior on kappa j, which is 1 over 1 plus lambda j squared, then the induced prior for kappa j is the beta half prior. You can see clearly that kappa j lies between 0 and 1. And so the induced prior on kappa j is beta half, and that has this horseshoe kind of a shape. Okay. So that's why it's called the horseshoe prior. All right. So, without going into the details, just want to mention that another reason for its popularity is that many nice theoretical properties have been shown for this prior, right? And this is just 3 references where this has been done. All right, so now hopefully we understand roughly at least what global local shrinkage priors are, what horseshoe prior is, and roughly why is it so effective and popular, right? Great, so we have a Bayesian model, we have the regression model, and then we have the prior on it, the horseshoe prior. So what do we want to do in any Bayesian model? We want to do posterior computation. We want to compute expectations with respect to the posterior distribution, quantiles, whatever, right? So that's the goal. We want to compute expectations or quantiles with respect to the horseshoe posterior. And I'm going to denote this horseshoe posterior by, pi h given y, right? And and this is where what Vivek kind of talked about in his presentation helps me out. So he said that, for many cutting edge Bayesian models, the posterior density, it's not tractable in the sense that you cannot do closed form computation, like the integrals or the expectations that you want to evaluate, they are just not available in closed form, or even direct IID sampling, like Monte Carlo sampling. It's just too computationally expensive to do it, right? And so the only resort that you have in these situations is MCMC, Markov chain Monte Carlo, where, as Vivek said, we find a Markov chain which converges to your posterior distribution as its stationary distribution. Of course, as one of the questions asked, well, you are going to get dependency, but computationally, at least, it's going to make your procedure viable. Okay, so you're sacrificing this independence for a little bit of dependence in the Markov chain, but at least computationally you're able to do something, right? And that's a trade-off people will happily accept, right? And so for the horseshoe posterior, several Gibbs sampling, and again, some of you might not be familiar with what Gibbs sampling is. You will understand as we proceed. So several Gibbs sampling based Markov chains have been proposed in the literature. Here are a few references. Okay. Okay, so you have the horseshoe posterior, and one needs to use MCMC to generate samples from this posterior or to compute posterior expectations. And people have proposed various Gibbs sampling Markov chains to sample from the posterior, right? So where does geometric ergodicity come in here, right? So let's say that this beta m sigma m squared, as m goes from 0, 1 up all the way to infinity, denotes one of these so-called Gibbs sampling Markov chains from the last slide. And let's say it's a Harris ergodic Markov chain, and it has this horseshoe posterior as its stationary density, right? All right. So what is the idea behind using a Markov chain? That our ultimate goal is to evaluate this kind of a posterior expectation, right? Let's say I want to evaluate the posterior expectation of a function g of beta and sigma squared. That's my ultimate goal. The Markov chain is just a means to approximate this ultimate expression that I want, right? And what enables this approximation? Well, if you can show that your Markov chain is Harris ergodic, then what you can show is that if you take these means of the iterates of the Markov chain, so if you look at the first m-1 iterates of this Markov chain, and you take the average of the function g over these m-1 iterates, then Harris ergodicity implies that this mean is going to converge to the population mean, so-called, right? So this Markov chain mean converges to the population mean. The caveat here is that these beta j sigma j squares, they are dependent. Okay, so you need ergodic theorem here. The strong law, it's for IID random variables doesn't suffice, right? Great, so you have an approximation for this quantity that you really want to understand. But again, as Vivek said, as statisticians, whenever we provide estimates or approximations, we always think about how good is this estimate? What is the standard error, right? So that is a question that immediately comes up. You are going to use these for an appropriate M. You are going to run the Markov chain, and then you're going to use this Markov chain average as an approximation to your posterior expectation. But how good is this approximation, right? And so what you need is you need some kind of an estimate of the standard error of this G bar M, the Markov chain average, which I denote by G bar M here, right? And for that, you need the existence of a Markov chain CLT, which is going to tell you, so this is like a parallel of the IID CLT, which tells you that after scaling with square root M, the difference between the estimate and the truth, it converges in distribution to a normal with mean 0 and this asymptotic variance sigma G squared, right? So if you need the existence of a Markov chain CLT, and then I think that's going to be the third lecture in today's session. There are various techniques. Once you know that a Markov chain CLT exists, then there are various techniques out there to try and estimate this in a reasonable fashion, the asymptotic variance sigma G squared, right? But the question is, how do I, so this is the form, I think Vivek also had this on his slides, the form of this asymptotic variance. And as you can see, it's not a trivial problem to estimate this. There is this infinite series and lots of careful work needs to go into estimating this. But we are going to focus ourselves on the question of how does one make sure that a Markov chain CLT exists, right? And one of the most standard ways, and possibly the only general way that I know of establishing that a Markov chain CLT exists is to show that the Markov chain under question is geometrically ergodic. Okay, and what does that mean? It means that we know that the reason why this Markov chain approach is working is that the distribution of this Markov chain converges to the stationary distribution, which is our posterior distribution, as the number of iterations increase to infinity, right? What geometric ergodicity tells you is that this convergence in distribution is geometrically fast, okay? Exponentially fast as the number of iterations increase, right? All right, and so really cutting the long story short, if you want to take home message from this part of the talk is that proving geometric ergodicity helps rigorously establish the asymptotic validity of CLT-based standard error estimates that MCMC practitioners need to use. So although this is a theoretical, technical concept, it is very important to practitioners because that is how they can justify the standard errors that they provide for their MCMC estimates. All right. So this is absolutely crucial if you worry about standard errors or validity of standard errors, right? Okay. And Vivek and Dutika, my co-speakers, will agree that both of them are experts in this area too, that establishing geometric ergodicity for the cutting edge continuous state space Markov chains that we see in statistics is not a piece of cake, right? It can get quite non-trivial and quite challenging. In fact, I would say that for a large majority of Markov chains that arise in these complex modern statistical applications, geometric ergodicity has not been established. In this global local shrinkage prior and also other contexts, there have been many success stories, right? However, for some reason, and this was something that puzzled me for a long time, the horseshoe prior. So for almost all of the global local shrinkage priors that I listed a few slides ago, in the last decade or so, people have been able to establish geometric ergodicity of these Gibbs samplers. Again, I owe you what a Gibbs sampler means. It's coming up right next. Geometric ergodicity has been established, but somehow for the horseshoe prior, even after I knew many people who were trying to do it, but it just wouldn't work out, right? So it was kind of the last man standing in this area of proving geometric ergodicity for, right? And the reason, at least intuitively, we could see the reason was precisely this nice property of the horseshoe, right? Which is that the marginal distribution of this beta j has an infinite spike near 0, and it has extremely heavy tails, which make the horseshoe prior very desirable. Precisely this algebraic structure makes it really hard for the geometric ergodicity argument to go through. All right. So that was the reason why this geometric ergodicity for this prior was quite elusive for many years. But okay. Okay, all right. That's what I said. But just in the last year or so, there has been a sudden activity in this area. So there have been 2 or 3 results, one after the other, proving geometric ergodicity for different Gibbs samplers for the horseshoe prior. So the first success, I would say, was by this paper by John Rowe et al., who established geometric ergodicity of a 2-block Gibbs sampler. We are going to see what this Gibbs sampler is for the horseshoe posterior. However, their conditions were quite restrictive. So they assume that these local shrinkage parameters lambda j squared, they are bounded above, and the global shrinkage parameter tau squared is bounded above and below. So it's compactly supported, right? Progress was made, this is just maybe last two months ago, this paper came out where geometric ergodicity was proved for the same Gibbs sampler. I call it the job Gibbs sampler after the 3 authors of this paper, John Rowe, Orenstein, and Bhattacharya. So that's the job Gibbs sampler. They showed that you don't need this lambda j squared, the local shrinkage parameters, to be bounded above. All you need is the global shrinkage parameter tau squared to be bounded above and below. So that's definitely an improvement, but still there is, this assumption of tau squared being bounded above and below can be thought of as something that you could improve, right? And so this is where the new result that I mentioned at the beginning of the talk is going to come in. We are going to prove a result which will improve this condition, okay, under weaker conditions, right? So before I do that, I want to now show you a little bit about this mysterious Gibbs sampler. What is this Gibbs sampler, and what particular Gibbs sampler are we going to use to sample from the horseshoe posterior? Okay, so our construction of the Gibbs sampler is based on this very, very nice and beautiful mixture representation of the half Cauchy. Remember, we are putting a half Cauchy prior on these local shrinkage parameters. That's the signature of the horseshoe, right? So what one can show is that if lambda j squared given nu j, so you introduce these variables nu j, is inverse gamma with these parameters, and nu j itself marginally is inverse gamma with these parameters, then marginally lambda j is going to have a half Cauchy distribution. So the half Cauchy distribution has this very nice scale mixture representation in terms of the inverse gammas, right? And therefore, if I introduce these nu j's, right, then the horseshoe prior can be alternatively written in this form. Okay, so here now I have vectorized things. So beta now is the vector of all the beta 1 to beta j. This lambda you see is basically a diagonal matrix with lambda 1, lambda 2, lambda j as its diagonals. Okay, and this is where this, instead of just writing a half Cauchy for each lambda j, I'm writing this alternative scale mixture representation. Okay, so it's a pretty straightforward alternative representation. And so now comes this 2-block Gibbs sampler, right? So now remember, how many parameters do I have here? I have beta, I have lambda, I have sigma squared, and I have tau squared, and then I have the nus, right? And so, yeah.
I'm sorry, sorry to disturb you and interrupt you. So yeah, so it's already 10:30 Indian time.
Right, I'll finish in 2 or 3 minutes.
That'll be great. Thanks a lot.
Yeah, sure, yeah, no problem. Right, and so what you do here is you basically block these 5 parameter into 2 blocks. Okay, this is your first block and this is your second block. Okay, and then what you do is in your Markov chain, if you are at this, then you go to the next step, which is beta sigma squared nu tau squared lambda, as follows. You first draw from the conditional posterior distribution of this block given the lambda, and then you draw the new lambda given this conditional. Okay, so that is the idea of the Gibbs sampler. You just divide your parameters into groups, and then you sample each group given all the others, and you keep on iterating. That gives you a Gibbs sampling Markov chain. Okay, that's the idea, right? So I'll just this is basically just showed in picture what I told you, right? And all these conditional distributions turned out to be standard distribution, normal or inverse gamma, all right? And what we show is that for this 2-block Gibbs sampler, one can establish geometric ergodicity by just assuming that this global shrinkage parameter tau is bounded below. That's all. That's all you need. And then you need a very, very weak moment condition, which is essentially satisfied by almost any prior that you can think of. All right. So really the only condition we need is that the global shrinkage parameter tau is bounded below. All right. And you can establish geometric ergodicity. Right. So I will, in the interest of time, I will just skip the simulation part of it. And let me just conclude by saying that hopefully what you take away from this talk is that, high dimensional linear regression is a very topical and modern problem. And for the Bayesian approach to it, the global local shrinkage priors, and in particular the horseshoe, remains a very popular choice, right? And for all these priors, posterior distribution is not tractable, so you have to use MCMC, right? And when you use MCMC, establishing geometric ergodicity is something that's really crucial, as it guarantees asymptotically valid standard errors for your MCMC estimates. And what we saw in this talk was that we saw one such example of a geometric ergodicity result for the horseshoe. All right, I'll stop here. Thanks, Vivek.
Thank you, Satish. I know it is past midnight at Gainesville. Thank you for staying up and giving this great talk. So there are a couple of questions on the chat. I will just read to you. So the first question was can you please reflect the intuition behind introduction of spike and slab prior? I think you mentioned that, but yeah, if you can say maybe.
Right. So you want to select you want variable selection, right? You want to select the significant predictors and you want to throw away the non-significant predictors, right? So to do that, you essentially want to introduce zeros or sparsity in the betas, right? And therefore, you use these spike and slab priors, which are a mixture of a point mass at 0. So that will help you introduce these zeros that you want. And then you have these flat or heavy-tailed slabs, which will help preserve the significant coefficient. So that's the intuition, that you have these two components to your mixture, which will help separate the coefficients into these two groups, significant and non-significant.
Another question was the asymptotic properties, do they hold independent of the choice of G and H in your priors? That was another question.
Yes, the geometric ergodicity essentially holds independent, as long as the distribution is truncated below, it holds for any distribution for tau. So that's the choice of G. And for H, no, for H, we are assuming an inverse gamma prior for H. But for G, any distribution that's truncated below works.
Thank you so much. Thank you so much. It's past midnight and
no problem.
You're an excellent talk. So our next speaker is Ritika Vats, who is an assistant professor in Indian Institute of Technology in Kanpur, where he joined in 2019. Before that, he was an NSF postdoctoral fellow at University of Warwick. Before that, he was a graduate student at School of Statistics in University of Minnesota, 3 hours away from me here, where he graduated in 2017. So Ritika, it's so we are I think 6-7 minutes past past 10:30. So you can go another 5-6 minutes after 11. I think that should be okay. So yeah.
Okay, I'll try and keep it as short as possible though. So let me initiate my share. Okay, and is this visible in full screen? Are you okay?
Yes. Yes.
Okay, excellent. Well, thank you to the organizers. Thanks, Vivek, for thinking of me for this talk. And it's quite nice to meet both you and Kshitij again after, even though it is virtually, and we hope to be able to move around soon enough. So I have the luxury of it not being midnight, and it's a reasonable hour for me. So hopefully I'm able to make some sense, more sense than I usually do. So Vivek set things up really nicely in setting things up for Kshitij as well as me and what I'll be talking about. And Kshitij set things up really nicely, focusing on the theory and convergence properties of Markov chains. What I wanted to do then was almost sort of go into the shoes of what a typical user finds themselves in. And typical user finds themselves with a Markov chain that they don't know much about, and they have to rely on visual tools to be able to understand the quality of such Markov chains. So some of this is going to be, I'll just talk about the standard tools of what we want to look at when we're looking at visualizations. And some of this is going to be new work that is, in some sense, seems elementary, but is based in a rigorous theoretical framework that underlies these Markov chains and study of these Markov chains. So, oops. So just a quick shout out to make sure I give due credit everywhere. So the first project I talk about was led by Medha Agarwal, who's an undergraduate student here, and she's hopefully heading on to a PhD very soon. And then the second project I talk about was headed by Nathan, who is a PhD student at Riverside, and then also James Flegel, who's at Riverside, and Galen Jones, who's at Minnesota, are the other collaborators on some of these ideas and visualizations that we want to focus on. Okay, so like Kshitij set up and Vivek set up, the theoretical study of MCMC samplers, it's important. Myself, I've done enough work in it, and that's an area of interest that's going to continue to be important. But it's often not possible to do that for generic MCMC samplers. And so visual aids that can qualify, not necessarily quantify, but qualify the performance of an MCMC sampler are going to be very important. And a key disadvantage of using MCMC is that MCMC produces serially correlated samples. And to sort of, in case there's any confusion, we don't want correlated samples, certainly, but we are in a situation where we can only get correlated samples, so to say, okay? And so because these are serially correlated, one after the other, there's a high amount of correlation that's in my Markov chains. Studying this correlation is very, very important then. Because if I can study and quantify or qualify that there is a large amount of correlation, that implies that my Markov chains are far away from being IID. And if there's small amount of correlation, that means my Markov chain is closer to being IID. And I know IID-ness is a desired property for me to have. So qualifying this sort of serial correlation then kind of comes back to a key property of a Markov chain. The Markov chain, which I will denote by X sub T, is the lag K autocovariance, which Vivek demonstrated via autocovariance plots, which is something I'll talk about in a fair amount of detail. So a key property are these lag K autocovariance, which I denote by gamma K, which is nothing but the covariance of X1 and X1 plus K. As in, it is, if I look at a time gap of any K time units between X in my Markov chain X, what is the amount of inherent covariance that's there in my Markov chain at that time lag? Right? And of course, that's just the expectation of X1 minus mu times X1 plus K minus mu, where mu is the mean of my underlying distribution. Okay. And I want to be able to study this lag K autocovariance for varying K, because if for large K, gamma K is large, that means there is serial correlation that is of a high degree. Because for large K, there is a large amount of covariance. And if for small K, gamma K is small, that means that I have samples that are close to being IID at least. Okay. Now, if I want to estimate gamma K, because I know that that's a key quantity for me of interest, I can estimate that using my standard sample estimate. So mu, recall, is the mean of my target distribution, and I'm estimating that using the sample mean, X bar. So the standard estimate is just going to be the sample estimate that matches the population quantity, and that's gamma hat K, which is just 1 over n, all the instances
Rutika,
of, yes.
Sorry. So did you change your slide? We are all seeing only the first slide.
Oh. Okay. I have not, but let me stop sharing and start again. Thank you for pointing that out. Okay, now can you see my slide?
Yes, yes.
Okay, perfect. So just for visual aid.
Yeah. It is changing now. Good.
Okay,
good.
perfect.
Thank you.
Perfect. Okay, so just so we're all on the same page, gamma k is my lag k autocovariance. That is the covariance between x1 and x1 plus k. That's really what I was pointing to. Thank you for pointing that out, Vivek. It would have been a shame to go through the whole talk with that. Okay, so and my estimate of this gamma k quantity over here, which is the population quantity in expectation, is my gamma hat k, which is the sample version of that population quantity, where I just accumulate all instances of k lag differences that I have, and I average that, and I replace mu, which is my population quantity, with x bar, my sample quantity. Okay, so that's my sample autocovariance, and that's typically used very heavily in MCMC, also in any correlated setting, typically also in time series, for example. Okay, and then once I have the sample autocovariance, I can also construct the sample autocorrelation, which is just gamma hat k divided by gamma hat 0 at k equals 0. And then we can plot k versus rho hat k, which is the sample autocorrelation, to get the autocorrelation function plot, or the ACF plot. Right? And this is exactly what Vivek had showed. And let me just show you an instance or two instances of good and bad Markov chains that produce good and bad autocorrelation plots. I'm not telling you what Markov chains these are, but on the left-hand side, we have a low correlation situation where as the lags increases, the correlation drops pretty quickly, and there's hardly any correlation beyond 20 lags. And that's an instance of a good chain. If I and Kshitij and Vivek will certainly agree with me, if I see a Markov chain that exhibits this amount of autocorrelation, we'll be fairly happy with this performance. Okay? On the right-hand side, we have something that we could quantify as a bad chain, in the sense that even beyond 40 lags, there is a correlation that is about 0.7. That means if I look at X5 and X45, for example, or X44, yeah, 45, sorry, I can't do math clearly. And at that lag difference, I still have sufficient correlation between this of about 0.7. That means that the Markov chain is slightly moving slowly across my space. It's not moving very quickly, that even in 40 steps, it's not able to move far away from where it was before. Okay? So that's an instance of a bad chain and an instance of high correlation setting. Okay. These are just to show you what an ACF plot looks like, and the fact that looking at these plots can actually give users a sense of either panic or a sense of calm as to, do I have a good chain or a bad chain? Okay. But now let's look at a particular actual example of a particular actual target density. Let me look at a Gaussian mixture target. So at the bottom over here, I have f of x is the density of my target distribution, which is a mixture of two Gaussians with 70% mass on the first Gaussian, which is this part, and 30% mass on the second Gaussian, which is this part. These have different means and slightly different variances. And I'll use a Metropolis-Hastings algorithm to sample from this target. And thanks to Vivek's first talk, I'm not going to have to go into too much detail of what the Metropolis-Hastings sampler is going to look like. So I can feel free to skip that in the interest of time. But essentially, I can choose a starting value x0, and then just propagate my Markov chain based on the Metropolis-Hastings algorithm and get subsequent samples from this mixture of Gaussian's target density. Okay, and I just described the MH algorithm here. But in practice, what we often do is we often run multiple Markov chains from different starting values. And the reason we can do this quite easily is on any personal computer these days, there's at least 4 cores available to us. One core we are typically using for a GUI interface, let's say. And so we can easily run a Markov chain on the 3 relatively free cores, as long as we're not watching too much Netflix, for example, right? So we can run 2 to 3 parallel simulations without any trouble. And in the same amount of clock time, 2 parallel runs of the Markov chain can run very effectively. And of course, if you have large number of cores, you can do this in a multiple format, utilizing multiple cores very efficiently. So typically, the practice is that we can run multiple Markov chains at least in the same amount of clock time, if not computation time. And so, for example, in this particular target density, I will choose 2 different starting values. I will run 2 different Markov chains. So let's look at how these Markov chains look like. So I show you a trace plot of a Markov chain for 1,000 steps. The blue trace plot, the trace plot was shown by Vivek in the first talk as well. is a flip trace plot where as I go down, time is increasing. And that's the blue part over here, which is this area of the Markov chain, chain 1. And in the pink chain, this is chain 2. And so both chains are starting at different modes. And in 1000 steps, they're not able to really jump the modes, right? In at least 1000 steps. So each chain is centered around its own mode and has not been able to jump across in the state space. And this is not good, because we would like each Markov chain to be able to eventually give us representative samples from my target distribution. If I were to not run chain 2, if I just looked at chain 1, I would not know that there is a whole mass in this particular area. If I were to not run chain 1 and only run chain 2, I would not know there is a whole mass in this area on the first part, right? So we know that at this point, we don't really have a good Markov chain because it's not able to jump across very freely. It's behaving in some restricted way. But if we were to look at ACF plots for these Markov chains, what these ACF plots are going to tell us is that we actually have a great Markov chain. So the ACF plot in chain 1 and an ACF plot for chain 2 both show that there's hardly any correlation after about lag 10. Okay, after about lag 10 or 20, there's little correlation to be worried about. And so if we were to just look at these ACF plots, we'd think we have a great Markov chain to fiddle around with. But if we looked at the trace plots, we'd see that we don't have a very good Markov chain. So what is really happening with these ACF plots? Why is it so that these ACF plots are not able to tell me that I have a bad Markov chain to begin with? And the reason is the following. Recall that my true gamma k, my true autocovariance, is the expectation of x1 minus mu, x1 plus k minus mu. And I'm replacing this expectation with a sample average, where I'm replacing mu with the sample mean x bar. Now the issue is, for the blue chain over here, the sample mean mu is a bad estimate of the population. Sample mean x bar is a bad estimate of the population mean mu. And for the pink chain, the sample mean for the pink chain is a bad estimate of the population mean mu, because they haven't as yet talked to each other. They haven't jumped around. And so what's happening is, for each chain, the variability is being measured around its own sample mean, which belies as to what exactly the underlying variability is in the problem. And so each of those chains thinks that the mean is fairly close to where we are. And so the variability is highly underestimated. And that kind of filters into the autocorrelation function plot. Okay. So we, as people who are working in MCMC, we rely on ACF plots all the time. But this is an instance where we can see that an ACF plot is clearly lying to us because of the fact that it's not able to capture the complex nature of what's going on in different Markov chains. And I know that the truth is different. The truth should be that they're not actually that well behaved, because if I run the Markov chains for now 100,000 steps, now each of the chains have been able to flip around and move from one node to the other. And now for this, the ACF plot looks like, indicates that there is slow mixing, that the Markov chains are not well behaved, where the left-hand side plot shows that there is a high amount of correlation and the right-hand side plot shows that there is a high amount of correlation. Now, this is exactly the true behavior of the underlying stochastic process. This is exactly how much correlation there is in the chain. But in the short run, we were not able to diagnose this behavior. We were highly underestimating that the correlation associated with the process. Okay, so ideally, we should be able to pick up that this is the amount of correlation, even in a short run of the Markov chain, but we're not able to do that. So the question is, how can we come up with a fix? And this is where Medha's work comes in. And the way we fix this issue is a really simple fix, where we say that instead of looking at local means for each of those chains, we will look at global means for the all Markov chains that I have. So if x sub s comma t is the sth Markov chain for s going from 1 through m, then x bar s is going to be the sample mean of the sth chain. And let the overall mean be x bar bar, which is going to be the sample average for all of my chains. Now, using this, we define the globally centered autocovariance for the sth chain as the same in principle, except we're replacing x bar s with x bar bar. We're replacing the local mean with a global mean. Okay? And at this point, you can see that once I do this replacement, I am no longer measuring variability about the mean of that chain, of the blue chain and the pink chain, I'm measuring variability from the global mean estimate. And so each of the Markov chains are then talking to each other when these autocovariances are being calculated. And then I also get an autocovariance for each chain, and I can average that autocovariance to come up with a combined autocovariance estimate, and that's going to be gamma hat sub G. Now, if I go back to my previous problem and plot these globally centered autocovariances, in the top part, I have chain 1, and in the bottom part, I have chain 2. Now, in the short run, these autocovariances are able to diagnose that, yes, there's a very slow mixing Markov chain. There's a high amount of correlation. And this behavior is also backed up again in the long run as well. So the short run and the long run now look similar to each other, as opposed to there being a false sense of security before with the old ACFs that were there. And similar behavior is seen in chain 2. Okay. So we can also have another visualization of this where we can actually plot all autocovariances together. Instead of the bar plots over histogram style plots, I can just have a line where this solid line is the overall autocovariance, autocorrelation, instead of just each separate autocorrelation. And the dotted lines are the each individual autocorrelation from each individual chain. Okay. Just another visualization that's possible. So just and one more thing, the globally centered ACFs, so these are useful not just in these multimodal or contrived target distributions. In any sort of slow mixing Markov chain situation, we see that when chains are moving slowly around the state space, the globally centered ACFs are going to be much more truthful in their depiction of how much autocovariance or autocorrelation is in the chain. Now, once we've constructed these autocovariances, because the Markov chain autocovariance is a fundamental unit that is part of the whole problem, they are actually employed further along in the study of Markov chains quite rigorously. So they're used in ACF plots, but these autocovariances are also used in effective sample size calculations or integrated autocorrelation time calculations. And then they're also useful, like Vivek had pointed out in the first talk, in Monte Carlo standard errors assessment for a particular simulation problem. So let me just give you a little bit of insight of that and another visualization that's really that I think really helps users in understanding the quality of their estimation. And then I think I'd be done after that. So consider now sampling from a standard bivariate normal distribution using Metropolis Hastings. So nothing really complicated. I have a bivariate standard normal that I'm just going to use an MCMC sampler to obtain samples from. And on the left-hand side, I've obtained some samples. On the left-hand side, I have a density plot of the first component estimate. On the right, I have the density plot of component 2. And then the sample mean is depicted by the blue vertical line. This is a standard bivariate normal, so the true mean is 0. So my estimate should be around 0, which is where they are. But the thing is, this is a MCMC simulation and Monte Carlo simulation is one that happens on a computer, and there is randomness and variability associated with it. So if I repeat this simulation again, I will get different estimates of the density and different estimates of the mean. So here's a depiction of another one. When I change the simulation, I repeat this again, I get a different density estimate. And if you look at the vertical blue lines, they're going to start moving. So I'm going to keep repeating the simulation. And these vertical lines of the mean, sample mean, keep moving. That means every time I repeat the simulation, just by the law of statistical variability, I'm going to continue to get different estimates of what's going on. And because I'm getting different estimates of what's going on, I want to be able to understand how good my quality, what is the quality in my estimation in my current simulation, right? And so naturally, I want to be able to know how do I represent this variability that is inherent to my problem without actually repeating my simulations multiple times. I don't want to have to sit on a computer and just keep repeating simulation just to understand my variability. Can one run of the Markov chain or a few parallel runs of the Markov chain just tell me this variability on its own? Okay, and we can do that. We can understand the variability visually by obtaining simultaneous confidence intervals. So here I give you the same estimated density with a vertical line showing you the sample mean for each of the components. and a confidence interval, which is in this purplish color, that's around each of the sample means. But these are simultaneous confidence intervals, which means that this the right and the left confidence intervals together have a simultaneous coverage of the desired 95%. Okay. And so this indicates how much variability there is in my mean estimate. And if this looks like this is too much variability, then I want to go and get more samples. And if it looks like it's actually reasonable amount of variability, then I may be happy with this number of samples. At least visually, when we are sharing these plots and density estimates in our papers and in our work, visually, it's immediately able to tell us what is the quality of estimation without looking at a bunch of different numbers. Now, this looks really simple. It looks, if we go to classical statistics, it looks like great. We have a sample mean and we have a standard error. We can just plot the confidence interval. But actually, it's not very simple. And there's two challenges over here. One is that we have MCMC samples, and both the speakers have alluded to the fact that standard errors and variance calculations from these MCMC samples is a highly challenging problem. And the second is that these are simultaneous confidence intervals. And that means together, we want how many of the confidence intervals we are making, we want them to have joint exact coverage. And that itself is a challenging problem as it is. Okay. But what is the framework of making these confidence intervals? A lot of the framework is dependent on utilizing a limiting normal distribution for my sample quantity. So if a Markov chain CLT exists, and that's a big if, and Kshitij just talked about a sufficient condition of showing geometric ergodicity to give us the potential Markov chain CLT. But if it exists, then we have that x bar square root n x bar minus mu converges to a multivariate normal distribution, depending on what is the dimension in which this mu vector lies and my target distribution lies, with a limiting covariance matrix sigma, and that sigma takes this form of the infinite sum of the lag k covariance matrices. So these are now P by P matrices, but it takes the infinite sum of these lag k covariance matrices. Now we know how to estimate gamma k because we've talked about estimating these covariances, but it should seem challenging that, okay, how do we estimate infinite lag covariances? And that's a really difficult problem. I won't have time to get into too much of those details, but I will hint at it. Nonetheless, we know now how to estimate gamma k's reasonably well, and we've improved the current estimation quality of it. So we can try and estimate sigma using gamma hat k's. Okay? And so that's exactly what we do. And there's one particular estimator, that's the spectral variance estimator, that says, okay, I'm going to look at the sum of the gamma hat k's, but I'm not just going to look at a naive sum. I will actually look at a weighted sum. And I'll not really talk about these weight functions, but there are appropriate weight functions that fall in a family that lead to good estimates. And then I can't really do infinite summation. So I have to truncate at some point. And so I look at some summations going up to Bn, basically, in either direction of 0. So I can't really do infinite sums when I'm calculating a statistic. So I'll just look at Bn, which is a truncation point. And once I have this estimator, which is called the spectral variance estimator of sigma, it has potentially has some nice properties. And if it has additional certain nice properties, then the final quadratic form is approximately going to give me a chi-square distribution with p degrees of freedom, which means I can use this particular equation over here to now construct a confidence region around mu. Okay. And because it's a confidence region, that means I'm sampling this jointly and I'm studying it jointly, which means I'm going to get a confidence ellipse in 2 dimensions or an ellipsoid in higher dimensions. Okay? So this pink sort of ellipse that I have over here is my confidence region, which is the minimum volume confidence region that's come from this multivariate construction. But then these blue boxes is what I would get if I were to do univariate confidence region construction, which does not look at the problem in a multivariate nature and just constructs univariate intervals for each of the components. And then the red one is going to be the corrected one that I correct for via Bonferroni correction, because I know the blue box is not going to have my right 90% coverage if I'm making 90% confidence region. But recall in the plot that I showed you before, I wanted a simultaneous confidence interval. And so this blue box, because it's a Bonferroni corrected box, the red box has high coverage and the blue box has low coverage. So somewhere in the middle on this black line over here in the upper right corner is a box or a half width which will give me approximately 90% coverage. Okay. And so actually how we find that box is slightly complicated, and time does not quite allow me to get into those details. But there's basically an optimization problem where we search on this particular half width line for the box that approximately gives me a 90% coverage. And once I have that box, then I can basically project that box down on component 1 and project that box down on component 2 to get what that interval looks like. And the reason we have to do this is because a confidence ellipse is great, but we can't take a confidence ellipse and use that to construct individual marginal friendly confidence intervals. And so we have to appeal to rectangular boxes. And in order to do that, we have to go in and find a 90% coverage box over here that would work out. And this is exactly what we do to actually get this particular simultaneous confidence interval where both of these together are the 95% desired coverage. The thing is, we can also do this for both means and quantiles. And again, I'm not going into the theoretical construction, but by very carefully constructing, obtaining asymptotic normality of both means and quantiles together allows us to actually plot standard error bars that are all simultaneous confidence intervals for both components for 2 different quantiles and the mean. So we see 6 intervals on here. The blues are the quantiles, 10% and 90% quantiles, and the purple in the middle are the mean confidence interval. And all 6 of these are simultaneous in nature. That means the coverage associated with all 6 of these is about 95%. Okay. Now, when I look at this, visually speaking, just as a tool of visualization, I know that I have my quantiles are way too variable, and I need more samples in order to estimate the density properly in order to get an understanding of what my multivariate normal target looks like. So I'm going to run more samples now and then visualize my Monte Carlo standard error via these simultaneous intervals. And with a much longer run, in the vertical lines are the estimated quantiles, and there's a very light shaded region that's hardly visible because the Monte Carlo variability has dropped down in a long run, and we can no longer visually see the margin of error associated with them and the simultaneous confidence interval. So at this point, we know that we're doing a reasonable quality of estimation. And at this point, visually, we know that we're not doing a reasonable quality of estimation. If we just had the density plot visible to us, we would not have been able to diagnose this problem. So I'll just wrap things up very quickly. One thing I have not talked about is that although these visualizations seem superficially simple enough, there's actually a fair amount of theory that underlies all of them. And so Kshitij and Vivek both talked about the need and the existence of a CLT without which it'll be very difficult to do reliable inference. And so questions about when does that hold are very critical. The new autocovariance function, the new autocovariances need to be consistent and well behaved, and we show properties of that. Estimators of sigma need to be strongly consistent, and there's a whole field where we want to understand under what conditions that holds. Sigma is a very, very difficult quantity to estimate and is riddled with underestimation in practice. And so quantifying that bias in the estimation, correcting for that is a big area and a need for the hour in my view. And then also these weight functions in this B and all these tuning parameters, how do you choose them so that they're theoretically good and practically efficient is a big area of study. And finally, anything we do in visualization should be shared to actually in open source, at least in my personal view. And for students, I'd tell everybody, if you make something that people can use, then write code and make it shareable. And so the ACF plots that we constructed are on the GitHub repository multi-chain ACF, and the paper is currently under review. And then the simultaneous visualizations, we're working on a big package that has additional features in addition to these visualizations that should be coming up by the summer, and that's the SimTools package that should be there both on CRAN and GitHub. So thank you, and I'm happy to take questions if we have time. Sorry, I did go slightly over.
No, you started late also, so no problem. Thank you. It was a good talk, and so there are a couple of questions. I'll just read it to you. The first question was, how much correlation we can tolerate? I think, autocorrelation, the person meant. Yeah.
So it really depends on many questions. So this is not a very simple question to answer. It depends on what your resources are, how much time do you have, do you want your samples to be done in 10 minutes. And if you have highly correlated samples, that means 100 draws of highly correlated samples is close to having no draws at all. Right? So you have to basically understand you have high amount of correlation. That means you'll have to run your Markov chains for much longer to get the same amount of information as IID samples would have given you. So it depends on how much information you have available and how much resources you have available as well. And Vivek in his talk summarized this concept of effective sample size and used it to understand the quality of the MCMC samplers that were being studied. And so that's one of the tools that's used to understand, do we have good enough samples when we've accounted for all this correlation or not? So it depends on the resources you have available. And yeah.
And so there are two, okay, so basically one there was another question, how can one choose BN in practice? And yeah, I think you mentioned it already, but yeah, if you want to add anything.
Yes, so this is a very good question, one that is certainly actually a very rich area of research in time series. Traditionally speaking, in time series, that's a rich area of research, and I've been working on that in MCMC as well. I mean, a safe rule is to sort of choose BN to be square root n, and that typically gives you reasonable performance. It can be a bit wasteful sometimes, and there's some literature that sort of says that that you can use more informed choices of BN, but a safe rule is to use square root n in practice at least.
Yeah, I think that's all the questions. So if anybody else has any other questions, they can ask now directly or send it by chat.
So it seems that there is no more questions in the chat. So if you don't mind, may I ask you one question?
Oh, please, sure.
Oh, okay. So this is basically for the data science practitioners. Like we all know that even for very simple model, for example, if you just have a simple random effects model, you can take some suitable priors for which you can very nicely run a GIF sampler, but essentially your posteriors is not proper. So essentially what you are doing, as shown by Hobart and Casella, I think long time back. So nowadays people in data science, they're like routinely using MCMC, but can you just give some recommendation, some simple recommendation by which at least they can convince themselves that whatever they are doing, it's not meaningless. In other words, they are not actually sampling from an improper distribution or something like that.
That's a very pertinent question. I'm certainly going to give this off to Vivek in a bit because I know he has good opinions about this. But one thing I will certainly show in terms of visualization, I think I've used these plots now recently in the past 2 months, and one particular instance of a particular Markov chain we ran it for about 10,000 steps, and we saw this plot, and then we continued running it for about 1 million steps. And we saw that these quantiles were actually, the variability was not reducing at all. And that was indicating, because I mean, you go from 10,000 to 1 million, at least a square root n sort of reduction should happen. And when we visibly saw that that was not happening, that indicated that this was an instance that where a CLT was not holding, that an asymptotic variance was not, my asymptotic variance was potentially not finite, even if the posterior was proper. I mean, assuming the posterior was indeed proper, we did have proper priors, etc. So visually speaking, if you don't sort of see this sort of, root n sort of convergence in your standard errors, then that's indicating that there's something else going on. But technically, I think Vivek can answer this much better.
Thanks, Dhutika. No, so as you already mentioned and referred to, Hobart and Casella's paper, in that 96 JASA paper, they already showed they showed that for an improper posterior distribution, that is when the posterior distribution does not exist, does not integrate to a finite quantity, then also if you can run a GIF sampler, they ran a GIF sampler, and they showed that if you plot that GIF sampler, if you see the trace plot, it looks fine. I mean, it looks fine in the sense that doesn't give any red flag that there might be something wrong with the posterior itself. So yes, so we can do all these visual diagnostics, and that's, and as Dutika mentioned, in in practice, many cases we can't do theory. I mean, we have to rely on these empirical diagnostics, visual diagnostics, and different empirical diagnostics measures. But we also have to be aware of the shortcomings of these measures, because as you referred to that paper, so you can run a Gibbs sampler, you can plot the Gibbs sampler, but the posterior may not exist at all.
Yeah, thank you. And I just have another question for Kshitish. I don't know whether he's there or maybe it's too late for him.
No, I'm here.
Okay. Okay, Kshitish, I just have one quick question. So I'm just giving you 3 different situations and just wanted to know whether the performance of horseshoe prior in terms of variable selections will be similar in the 3 contexts. In one case, we have 50 predictors and 5 of them are important. Second case, I have 500 predictors and 50 of them are important. Third case, I have 5,000 predictors and 500 of them are important. So my proportions remain same. So do you recommend that horseshoe priors will be equally effective in all these 3 settings?
I mean, generally, these variable selection methods are more effective when the less the less the proportion of truly significant variables, they'll be more effective. That's a general rule, Of course, there is lots of other things that need to be taken care of. So the situation where you had 500 predictors and 5 were significant, was that one of the situations you said?
No, I'm saying 50 predictors, 5 significant. Next situation, right. 500, 50. Next situation, 5,000, 500. So always 1/10.
Oh, I see. So it's just the proportion is the same, but it's just that
yeah.
Right.
So
but I mean,
similar.
Right. I guess it it depends on the sample size and all these other things too. But I think in general,
that's a generic thing. But for horseshoe, is there any specification?
Anything I'm not aware of any such thing that that the horseshoe specifically would change its performance if the number of predictors increases, but the proportion of significant ones stays the same.
I see.
Right.
So can I ask a question to the
sure.
professors? So as a practitioner,
right.
Why should I choose a Bayesian algorithm which seem to have a lot of computational overhead and theoretical complexities when simpler algorithms are available, like ElasticNet or for your particular horseshoe? Why should I ever use Bayesian for a practical problem, especially when I have a lot of observations?
Right. That's a very valid question, and that comes up all the time. And the standard response of the Bayesian community is you get uncertainty quantification for free with the Bayesian approach. So you get through the posterior, you are able to get these credible intervals for free, whereas that's not something that comes. If you use a frequentist approach, lasso or something, you will have to use either some sort of a bootstrap. Then you don't know whether it's really valid or not, especially in these high-dimensional settings. So that's the standard selling point, that with the Bayesian approach, you tend to put in extra computation, but then in return, you also get this uncertainty quantification for free, which might be useful.
But this uncertainty is with respect to subjective priors, right? Like there's a subjectivity in Bayesian probability, right?
Right, of course, and that's why there is this huge area which was developed as a response to this, was using these objective priors. The reference prior is one of them. There is a bunch of other things. So that is again a valid criticism. Of course, the Bayesians will say that, well, you believe in your information, and that's fine. But then people who don't like this subjective part of Bayesian inference, as a response to that, you have the objective Bayesian paradigm, where you put these non-informative objective priors, and then at least you have that that level of subjectivity is gone. So then you can use those kind of priors.
So can I come in, Kshitish? I just want to, understand the question of the speaker. So are you said that, you know, that when there are simpler solutions like elastic net, I don't know why you were saying that is simpler, because, so, you know, I mean, I can give you an example where I have 500,000 predictor, elastic net doesn't run, lasso doesn't run, those packages doesn't run, but a Bayesian, you know, with a Bayesian model, we can run it. We can get the variable, we can select the variables very easily. So I don't know, I mean, are you thinking of just hundreds of variables? Yes. But you know, when you go for what we are talking about, ultra high dimensional setting, it's not clear that elastic, when you say that, you know, when you have simpler solution like elastic net, I don't know what you mean. But
by simpler, I mean that, you know, see, I don't have to look at trace plots and check whether I've converged. I don't have to twiddle with the, you know, various parameters and ensure better mixing. And even after that, you know, it's on a rather weak, I wouldn't say weak, I wouldn't say very shaky theoretical ground, even at the end of all that. So, so that's all I meant. I'm sorry. Yeah, I'm just saying that for practical problems, isn't that a lot of overhead? That's all.
Could I come in as well? Just
Sure.
So I mean, because you mentioned the trace plots, etc., and in the theme of what the session today was about, it was actually not about Bayesian statistics, right? It was about Monte Carlo in data science. And the reason MCMC is very heavily used is because Bayesian statisticians employ them quite often. And so, but the session itself and the topics that were discussed hold outside of the Bayesian community. It's just that we're involved in the Bayesian world because that's where the models are employed. And so, yes, Bayesian models are challenging to actually make inference on, particularly because of the troubles with the computation. But that's not a problem with the models themselves. So, for example, ElasticNet seems easy, or relatively easy, so to say, because somebody figured out the optimization routine to actually get to the optimal solutions, and that optimization itself is challenging. But somebody's been able to figure it out, for example. But just to sort of highlight, because a lot of the examples today were about the Bayesian in the Bayesian paradigm. There's plenty, for example, generalized linear mixed models where MCMC is also used to sample the intractable distributions in a frequentist setup. And so it's not necessarily just a problem or just something in the Bayesian world. And this is a thing I grapple with all the time. So I just wanted to take the opportunity, when we have young people in the audience, students, to sort of disassociate MCMC from the Bayesian world and Monte Carlo from the Bayesian world. It's just a toolkit. It's just a tool itself to answer questions that are asked in the Bayesian community.
Yeah, that's fair enough. Yeah. Okay. Thank you.
Thank you, Dutika. And that's the reason in my slide, I had the likelihood function, which was interactable. I didn't have posterior.
Yes, exactly. Exactly.
Okay, so I think that's good enough for now. And thank you all the speakers for your time and for your nice talk. It's an excellent session. And I think the participants really learned a lot from this session. So I thank you once again, all the speakers. Thank you, the organizer, Vivek Da, for organizing this session. And so our technical session for this morning ends here. And our next academic sessions will start at 3 p.m. today. Thank you all. So participants, please join again at 2:45. Thank you very much.
Thank you. Thank you.